today we're going to be discussing derivatives of exponential functions. So we're going to be looking at exponential forms, base e and base a. So first off, the derivative with respect to x of e to the power x is actually equal to e to the power x. So it returns exactly the form that you had differentiated. This formula can also be obtained from first principles, so you can then check using your limit definition for computing a derivative. In addition, what happens if we had given you an exponential form base e, but with an exponent, some function g of x? Then of course computing this derivative is going to require the chain rule. So the derivative with respect to x of this function, now recalling what your chain rule told you, if you identify your inner function and your outer function, and here the inner function is g of x, which is in the exponent, and the outer function is base e raised to some variable. So the chain rule tells you that it's the derivative of the outer, which is base e raised to some variable, but we know it returns exactly the same thing, so something in the exponent. So it's the derivative of the outer evaluated at the inner, so I'm going to put back g of x and then times the derivative of the inner function. So the derivative of base e raised to some function is base e raised to some function times the derivative of that function. And so these are two important formulas for you to keep in mind. Now, what if we had to compute the derivative of base a times x, where we will impose that a is not equal to 1, for if a did equal to 1, then 1 raised to anything just gives you back the number 1. So there's nothing useful about the derivative of a constant. We already know what that is. So in this case, when it's not 1, we are now interested in finding out the derivative of base a raised to the variable x. So one way to actually compute this derivative is to make use of what we now know about the derivative of base e raised to the power x. So using a change of base formula, note that we can rewrite a to the power x as e raised to the power ln of a times x. Recall that e and ln are inverse functions of one another, so they undo what has happened here, and so we have that this is indeed equal to a raised to the power x. So this then means that the derivative with respect to x of a to the power x is equal to the derivative with respect to x of e raised to the power ln of a times x. And so we will now compute the derivative of this function in order to obtain the derivative of base a raised to the power x. So this is what we are now interested in. And we already know how to compute the derivative of base e raised to some function, because there it is there in step 2. So if you now accept that ln of a times x is your inner function g of x, we can now apply that formula to get out this answer. Now remember, a is some number that is not 1, so ln of a is a constant. So right here, ln of a is a constant being multiplied to x. So keep that in mind when we are now applying that formula. The derivative of this is going to be equal to e raised to the function, so we just copy what we have, times the derivative of the function in the exponent, which is a constant times x. What is a derivative with respect to x of a constant times x? It is just the constant. So that means we get back ln of a. And so that is the answer for differentiating this expression. So simplifying what we have, since we know that e and ln are inverses, we get back a to the power x times ln of a. And so we now have our formula 3, which tells you that the derivative with respect to x of a to the x is equal to a to the x, so you rewrite it, times ln of a, where a was the base in that exponential form. And just as before, where we had obtained some type of chain rule for this, we could then obtain a formula, I'll call this 4, for the derivative with respect to x of a raised to some function g of x. So again, using your chain rule, g of x is the inner function and a raised to some variable is the outer. So using your chain rule, it's the derivative of the outer evaluated at the inner. We know what the derivative of the outer is. It is that evaluated at the inner, which is g of x, times the derivative of the inner. And so this is our formula for computing the derivative of base a raised to some function g of x, where of course a is not equal to 1. So keeping this in mind, let's now look at some examples. Right, so I've got 3 examples prepared. Right, the first of which is to compute the derivative of the function base e raised to the power 3 plus 5x. So we want to compute y prime. So immediately observe base e raised to some function. So this is essentially e raised to g of x. So we know we're using our second formula in here. So that's what we're using. So the derivative of e raised to some function is e raised to that function times the derivative of that function. So we know the answer is e raised to the function times the derivative of that function. And so simplifying, we have that y prime is e raised to the power 3 plus 5x times the derivative of 3 plus 5x, which is just 5. So y prime equals to 5 times 3 times e raised to the power 3 plus 5x, and that's it. Now looking at the second bit, this is not base e, it's now base 7 raised to some function. So it's of the form a raised to a function, right, which of course now requires the use of that formula. So we know now that y prime is going to be equal to base 7 raised to that function, 3x plus 1, times ln of the base, which is 7, times the derivative of that function. So since I've called that g of x, I'm just going to write it down as g prime of x, and in the next step we'll now compute that derivative. So it's 7 raised to the power 3x plus 1 times ln of 7 times the derivative of 3x plus 1, which is just 3. And so you could either stop there, or if you wish you could then simplify if possible, but that is where we will stop. And then finally we now have the following. So observe, so this meant to say x, right? So this is y is a function of x. So x raised to the power 4 times e raised to the power 4x. So observe that we now have the product of 2 different functions. So this is like your u of x times your v of x. So whenever you have the product of 2 functions, immediately you will require the product rule. What does the product rule tell you? This then means that y prime is going to be equal to the derivative of 1 multiplied to the other, and then reverse what you just did. So the derivative of the other multiplied to the one that you previously differentiated. So that now means that y prime is now going to equal to, so since this is u and v, I'm going to take the derivative of x to the power 4. So that is 3x, sorry, that is 4x cubed. And now I'm going to multiply it to the second function, which is e raised to the power 4x, right? And now addition followed by the rest. So I now need to differentiate this portion. So what is the derivative of e raised to the power 4x? Remember, this is now going to require the chain rule version for the derivative of an exponential function. So that's what I'm using. So that's going to be equal to e raised to the power 4x times the derivative of 4x, which is just 4. And then I'm going to multiply it to that function, which is x to the power 4. And then you can see how much we could simplify. So here I've just got 4x cubed times e raised to the power 4x, and here I've got 4x to the power 4 times e raised to the power 4x. So I've observed that I now have common terms which I can now factor out. So I'm going to factor out 4, going to factor out x cubed, and I'm going to factor out e raised to the power 4x. what am I left with? 1 plus x. And so that is the final answer. So be able to use these new rules that you've learned from this first slide in conjunction with all of the other rules based on logarithms, the product rule, the quotient rule, and any other general basic rule that we've learned.